Thank you, Spencer. Thank you, Bill, for organizing this wonderful workshop. Today, I'm going to just give a presentation on what we see happening to Palynology near the Moscovian Kasimovian boundary, with some extension in both the Appalachian and Eastern Interior, which is informally known as the Illinois Basin. We in Kentucky and my colleagues in Indiana, which also have the Eastern Interior Basin, always like to point out that the official name is the Eastern Interior and not the Illinois Basin, even though they have most of the basin. Slide, please. I'm going to do this in reverse order. I'm going to start out in the Illinois Basin. So up on the top left, that is an outline of Pennsylvanian strata in the Illinois Basin. As you can see, most of it does occur within Illinois. You can see the position of it beneath that in the United States. The photograph below that shows that thanks to Pleistocene glaciation, Illinois is really, really flat. And so most of our work is either done from underground mines or more commonly through core, as I'm showing here. We simply don't have a great deal of outcrop exposure as we do in the Appalachian Basin. That's affordable to do any collecting or analysis from. So what I've shown on the right-hand side there, this is just a correlation chart of what we see within the basin. And most importantly, on the far right, where I have IB spore zones. These are by my, were formulated by my friend and colleague Russ Peppers, who has now been retired from the Illinois Survey for some time, but he made this up in the about the mid-1980s. I think it was first published in 1985. And what he did is he noted changes in spore distribution and introduction and termini of different Palynotaxa at various levels. So he constructed 11 Miospores assemblage zones. And I use these extensively. I think they work really, really well. I would point out that there's one thing that has been brought up, and I'm following up on this slowly but surely. All of these Miospore zones are based on coal only. And when you look at other assemblage zones constructed in Western Europe and elsewhere, quite commonly that they contain both coal and clastic lithologies. Now, on the surface, you might wonder, well, does that really matter? And the answer is yes, because what I'm finding is that a lot of the extinction points and introduction points of many taxa are either slightly above or below where they occur in the coal. So next slide, please. One of the benefits we have working in the Pennsylvanian is this is really thanks to people like Bill DiMichele, Tom Phillips, and a host of other people, Herman Pfefferkorn, Bob Gastaldo. We know a lot about the parent plants that produce the spores. And so this was the diagram of the lycopods or lycopsids there was drawn by a colleague of mine, Steve Greb, who is a very, very talented geologist and an amazing artist. So he took an earlier diagram and some other out of the literature from Bill and others and made this very, very nice reconstruction of what our major lycopod tree genera are like. So over on the far left, you have Lepidodendron. And what I've done is I've matched it up with the different, the spore species, genus and species, that we recognize it from in the Palynophora. So Lepidodendron produced Lycospora pusilla spores. Two forms, Synchysodendron and Diaphorodendron, produced Granosporites medius. Sigillaria, Crassospora kazanki, Lepidophlowis produced two spores in the Des Moines in the late middle Pennsylvanian, Lycospora granulata shown there. That is the dominant form in older strata, especially early and early middle Pennsylvanian. Another type of spore like Cospora pelusa is usually the dominant form. Paralycopodites produced Lycospora micropapillata, and one that I'm not showing here, Lycospora orbicula spores. And then you get into a subarborescent lycopod we call Omphalophloius, which curiously was named by David White back in 1898. And, you know, it's always perplexed me that I've never seen mention of it in the American paleobotanical literature since, although it does crop up in the European literature. And my friend and colleague Stan Aplustel has done a lot of work with Omphalophloius. Chalineria, which in my less than humble opinion goes down as the ugliest Pennsylvanian lycopod, was just a shrubby little thing, but it produced a very, very lovely spore, Endosporites globiformis, and some other species of Endosporites. And as with many plants, the smaller and less spectacular the plant, the larger and more spectacular the spore. Selaginella produced Cirrotriaridites spores. And then we have another one, Anacanthotrilades. This is attributed to a lycopod we know very little about. Carinostrobus was its mate, the cone that produced it. And it's only known from one spot, to my knowledge, of the early middle Pennsylvanian of Kansas. But this is really beneficial when we start to talk about these plants, because what I try to do is not to barrage people with a bunch of taxonomic names which really make no sense to other people than myself and some others, but to try to talk in terms of, well, these were the spores produced by this plant, which seems to work better. Next slide, please. And we do have others. On the top row, we have Thymospora, Levigotosporites, Torospora, Cyclograноsporites, and just below that, Punctatosporites minutus. These are all produced by tree fern spores. And one thing that we know about especially by the early Asturian, but especially into the middle Asturian, this was the zenith of tree fern spore diversity, not abundance, but diversity within the Pennsylvanian. We simply don't see these early in the section, lower in the section. And yet things like Punctatosporites minutus, which my master's and doctoral thesis advisor, Bill Gillespie, named buckshot spores because they're small and they're just everywhere. But we do lose a number of forms that I'll talk about here at the Kasimovian-Muscovian boundary. And then we get down to the spores that are microreticulatosporites and then going downward. These are small fern spores. And these are significant in that, you know, in the fern group, this is where we see all our diversity. But yet, when you think about a small fern in terms of biomass contribution, it really was quite insignificant. Slide, please. And then we go on to the top row, those are calamite spores, Vestaspora, Reticulatosporites, Calamospora, and down below that, both species of Levigotosporites. We do have conifer pollen in our assemblages, although it tends to be rather insignificant in terms of amounts. Pitiosporites, it's almost identical to modern pine pollen. Pseudoillinites is another one. And then, of course, we have chordate spores, mainly by the genus Florinites. And I forgot to label Florinites mediapudens above it. But we have a number of different chordate taxa as well. So this allows us to talk in terms of different types of, not only different types of spore taxa, but also in terms of the parent plants that were producing them. Slide, please. So and Bill kind of beat me to the punch here this morning. I'm actually going to start down a little bit, actually in the Balsovian. Because what we do see a big shift at the Muscovian-Kasimovian boundary, but it's preceded by a number of different events. At the and of what Russ calls his radius and 80s deformis assemblage that down in the trade water. We see a number of taxa disappear. This is where we start to see an increase in coal of mineable thickness, and these are primarily represented by the block coal interval of southwest Indiana. And these coals are one of only a few in the basin that have an abundance of low ash, low sulfur coal. Most of our coal elsewhere it tends to be low ash but higher in sulfur. These are dominated by mostly by lycospora, but also tree fern spores. This is where we start to see a big influx of tree fern spore taxa. And the radius in 80s is just a type of densospore, which was also produced by Amphilophloius, and it is confined to this interval, so it's a very good biostratigraphic marker. Next slide, please. Moving up into what Russ calls his Catiospora magna, Morosporites inusitatus, MI assemblage zone. Here we see the introduction of both spores that name this. We see the extinction of Dictyotriletes bireticulatus. One of the curious thing about the coals in the late part of the trade water that this assemblage defines is we see a spike in Floronites, and I've never really quite understood this, but we do see a lot more Floronites in this interval, but they're otherwise very similar in terms of lycopod and tree fern abundance. Here we see an increase in coal of mineable thickness again, but here we're starting to pick up an increase in sulfur. What I typically describe coals of the late trade water as being commonly high in sulfur and occasionally low, whereas the coals in the block coal interval of the underlying RD assemblage, they're commonly low in sulfur but occasionally high. And this is where we start to see the beginning of what we call a cyclothem deposition pattern that expands and dominates overlying Carboniferous strata. Next slide, please. Phil talked about this yesterday. I wasn't sure how familiar people are with cyclothem and the cyclothem deposition pattern. So I put this in, and this is just a graphical representation of one cyclothem. So you have peat formation occurring on a low stand underclay. You have a transgression, sea level rise in marine flooding, followed by marine seas. And then you see a regression pattern with coastal deltaic progradation. And ultimately, you go back into another low stand, and then the series at number 7 repeats itself. And all you have to do is work in the Illinois Basin for about 3 months, and you can see this time and time again. It's a very useful concept. Next slide, please. Marching upward, this is where the CP, the Shophites colchesterensis, Miospores pseudothecani zone, occupies all of the Carbondale Formation. And this is important because the Carbondale Formation has about 90% of the mineable coal in the Illinois Basin. It is extremely coal rich. Two of the major beds, the Springfield and Heron, our most recent coal reserve or coal resource calculations puts a combined estimate at just over 160 trillion tons of coal. That's a great deal of coal. Here we should note that Shophites is a very, very good marker spore because it's restricted to the Carbondale. We have seen the disappearance of many species of Densosporites, and in the Colchester coal, we see the last vestiges of Densosporites occur. I should note that subsequent work by myself with clastic strata show that these do occur, although not abundantly higher in the section. And here we have a very, very strong influence of cyclothem deposition. And I should note that these coals, and Phil touched on this yesterday, these are commonly capped or the overlying roof strata tends to be a very dark, organic rich shale that is also metalliferous. It contains a great deal of many different types of critical metals and other things. And what I mean by organic rich, TOCs on these are commonly in excess of 20%, 20 to 30% in some cases. Next slide, please. This is just an example of one of the Carbondale coals. This is the Springfield from Hopkins County, Kentucky. And what you can see over, because I've taken the 152 centimeters and I've lopped it down into 26 different intervals of the sampling, you can see that at the base of it, it starts out with a lot of Lycospora orbicula or micropapillata, indicating that Paralycopodites was probably important in this part of the bed. It makes a lot of sense because Paralycopodites probably was a pioneer type of lycopod. Just above that, we see the spike in small lycopsids, and this is that Anapiculatasporites spinosus, which we just don't know a lot about. And then you see an expansion of tree ferns through the rest of the coal, and importantly, Thymospora pseudothecinae, which then is transplanted by Punctatasporites minutus. And at the very top, you see what we call thick-walled tree fern spores, and goes by a variety of different genera. And at the very top, we see a pulse of Granosporites come in. So when you take the time and you break the coals down, you can see a great deal of change that's reflecting environmental change as the swamp matures and ultimately demises. And just lastly, chordates, in this part, I noticed, I mentioned that earlier, lower down, we see a lot of chordate pollen. We don't see a great deal of chordate pollen, but where we do find it, it tends to occur in these, what I call spikes. And again, it doesn't seem to match up with much else. So it's hard to interpret. Next slide. So this is the zone that is the last of the Moscovian, the Lycospora granulata Granosporites media zone. It does contain two of our last economically important coals, the Heron and the Danville, in the Illinois Basin. These two are tree fern, arborescent lycopsid dominant in terms of palynomorphs. And we do see an increasing amount of Granosporites medius in an overall perspective. And in contrast to the underlying coals of the Carbondale, these coals are usually capped by terrestrial clastics. We've lost our black shale tops. And then when we get to the very top, we see a number of things go out. Okay, so all of our lycopods, boom, gone out. Cirrotrieridites, depending on the species, this species, Enuliformis, it goes a little bit higher, but then it goes to, next slide, please. And it's not just the lycopods. We see ferns, okay, Triquetrides, Miospora, we see calamites, Vestaspora, and then, even tree ferns, Torospora securus, bang, that goes, and along with some other ones. But we do see the continuation of other spore types. Punctatasporites minutus keeps going, and it invades and becomes the dominant spore in the late Pennsylvanian. In the lycopods, we see the persistence of both Crassospora, which is sigillaria, and Endosporites. So we always talk about the lycopod extinction at this level, but it affects other plant groups as well. Next slide, please. This is just another rendition of the heron coal. Again, a very important economic coal. Here, I've noticed that we have two. The blue band is a clay-rich parting that extends across the entire area of the coal. Its origin is still uncertain, but probably is due to a base level rise and then deposition of very, very fine clastics. The steel band beneath it doesn't occur as widely. But in this particular case, this was a new KGS record of having 39% sulfur in the form of pyrite in it. And it's named the steel band because it has so much pyrite in it. And when the early miners with their picks and shovels probably had a lot of other colorful names for it. But you can see the same kind of pattern. You see Lycospora and Orbicula micropapillata common at the bottom, and then that gives rise to a more granulata dominant flora throughout. Tree ferns, same kind of patterns we saw in the Springfield, maybe a little bit different, but similar. And the same is true for the other plant groups. Next slide, please. This is the Baker coal, which is the Western Kentucky name for the Danville. And I just put this in to show that this, again, it's a thick coal that continues to be mined, not as much as the Springfield Heron, but you see the same kind of patterns going through this coal. But I didn't sample this in the fine scale benches that I did with the others, but the patterns are the same. Next slide. And then when we get up to the MO, LM, and TT, these are late Pennsylvanian assemblages. These are really based on abundance of different tree ferns, Palynotaxa. Some being more abundant in various things. But in addition to the tree fern taxa, we see a lot of Levigotosporites minor, which is a calamite spore. Endosporites globiformis becomes very important in certain beds. I know the Mason bed was, which underlies the Brush Creek coal in the Appalachians. It's especially prominent in that coal. And then we do see an increased influence in conifer pollen, and I've shown that here with Pitiosporites. Next slide. So I put this in because this was, Russ Peppers did this on the Lost Branch Formation, where he went in and he started at the Dawson coal and then sampled what were clastics and limestone up through and up to what was labeled as the Hepler coal. And I draw this to your attention because you see on the left-hand side, the Dawson coal is a co-dominant lycopod tree fern spore coal. The lycopsid spores diminish upwards, okay? And then when you get up to the Hepler coal, there we're talking mainly tree ferns, and in one of the benches there were some small ferns. And we also see quite a few calamites in that coal. But more importantly, if you look at the amount of seed ferns, chordate, and conifer spores and pollen, or in this case, that's all pollen, this is remarkable because we just don't see this elsewhere. And so one of two things could be happening. These could be just especially prevalent at this location. But the other thing is that these are all coming from clastic assemblages. These are not coal assemblages. And so I can't help thinking that that's playing a part in what we end up seeing in the Palynophora. Next slide. Now, over in the Appalachian Basin, we do have a great deal of topography, which affords us road cut exposures like this one. And so we don't have to rely on drill core nearly as much, so we can take pretty pictures like this. Next slide. I'm going to talk about, we're going to start in the Allegheny. At the top, we have the upper Freeport coal, and then at the bottom, the Brookville coal. In West Virginia, the Allegheny Formation is referred to in the northern part of the state, whereas in the southern part of the state, the interval is referred to as the Charleston Sandstone. And you can see some of the differences in coals there. So, next slide. Next slide. So these are just some spore patterns. Really, what I'm just trying to impress upon you here is they're very similar to what I just showed you for the Springfield, Heron, and Baker, which those are the primary equivalents. Okay, next slide. Again, this is the first slide, the previous slide was from northern West Virginia. This is from southern West Virginia. At the base, we have Balsovian coals assigned to the Kanawha Formation. But again, the same type of interplay with lycopsid and tree fern spores, and your occasional abundance of chordate pollen coming in. Next slide. This is from northeast Kentucky. Again, same type of distribution patterns. Next slide. And that's just the top of that section. Here, at the break between the Princess and Conemaugh formations, the Princess 9 is the last. Next slide. Oh, the previous slide. I'm sorry. Yeah, okay. Where you see Brush Creek and Bakerstown at the top, that's where we lose all of our lycopods. So your Moscovian, Kasimovian boundary is between the Princess 9 and the Brush Creek. And the rest of the slides are going to be all above this. So next slide. Here we have, this is our late Pennsylvanian, and at the base, this is the Glenshaw Formation, which is essentially the Kasimovian. We don't have a lot of coal in the Glenshaw Formation, and therefore it's not very well studied because there's nothing economic about it. The coals do typically tend to be high in ash and sulfur. And as Ron Martino mentioned yesterday, the limestones are mainly marine. One thing that I think is unique to the Dunkard Basin is that we have the overlying Monongahela group, which is Pittsburgh and Uniontown Formation. Here we have very, very thick, widespread coals that are low to moderate in ash, but high in sulfur, and a lot of limestones that are described as free, freshwater or non-marine. In both cases, the clastic strata that interbed with the coal are characteristically red-green in color. Next slide. And what we're showing here, this is of the Pittsburgh coal. This is up in the Gazellian. But what you can see here, this is the Pittsburgh is 2 to 3 meters thick, so it's very heavily mined. And what I'm trying to point out here mainly is that it's all tree fern dominant spores, and with minor amounts of calamite and other things. And one thing about the Pittsburgh is that where you see bearing in bench there, that is a higher ash unit. It's not very thick. It's only 5 to 10 centimeters in most places. But it extends across the entire area of the occurrence of the Pittsburgh coal. So it's definitely not a crevasse splay. It is something that probably is it's got to be either tectonic or climatic. Next slide. I haven't talked much about coal petrology. In addition to being a palynologist, I'm an organic petrologist. But one thing about most of the coals in the late Pennsylvanian, and this would include the Conemaugh coals, is that they do tend to be dominated by vitrinite. And one thing we know about vitrinite is that its formation is enhanced by anoxic conditions, or at least disoxic conditions. And that goes well with the increased occurrence of pyrite. Pyrite is an anaerobic mineral because iron in every case will always bond with oxygen before it results to bonding with sulfur. Next slide. And these are just two summary slides, just showing what how we can use palynology to break things down and use it for biostratigraphic correlation. Next. And that's just extending it through at least different assemblage zone criteria that I'm aware of. And those are the sections that we've talked about in the Appalachians. Next slide. And I'm sorry I had to rush through all of that. For those of you not familiar with underground coal mining, that is the business end of a continuous miner. And the two gentlemen in the back are about to swap out the little what look like bulbs on the cutting drum there. Those are the bits that they have to change out about once, at least once a day, depending on what they're cutting. So again, I thank you for your attention, and if there are questions, I will at least try to answer them.
Great. Thank you, Courtland. Thank you for that explanation. That's talk. It's great. Are there questions out there? John Knight, turn on your audio, John, please.
Can you hear me now? Am I on with you?
Yes.
I hear you, yes.
Yep, okay. Thanks, Courtland. Very interesting. I'm afraid, you know, I'm going to be banging on a bit because I've been fingered to defend the Cantabrian this afternoon. So you'll understand my interest. Looking at your sections, you're frequently using the Asturian as a substage of the European section. But of course, the Asturian has never been defined anywhere, neither its base nor its top. And the top, of course, will be defined by the lower stage of the Stephanian. Now, the reason I'm making this point was that your last slides, well, one of the last two slides, you were showing the European OT palynological zone, which was set up by Clayton back in 1977. But of course, if you read that, you'll see that the interval they were covering in that zone was across the Westphalian D, or Asturian, as you might want to call it, across a gap of 3 million years and into the base of Stephanian A, as defined in the Saar coalfield, including the Guttelberner Schichten. So that OT zone, mostly based on clastic sediment, very few coals, is, how can I put it, a very slanted picture of the stratigraphical change taking place in Europe at that time. So I guess to sum up my question, I mean, are those upper West European Palyno zones, the OT zone, the ST zone, are they any use to you, or are they just there as a sort of make the picture complete?
Can I answer that in about 15 months? I'd
like to wait.
I mentioned at the beginning of my talk that, you know, I regard Russ's work as really, really good. It's fabulous, but it is just based on coal. What I have done by working with Bill and several other colleagues in looking at clastics associated with the coals, I have noticed that the ranges that define those zones are often a little bit skewed upward or downward, or both in many cases. Now, with regard to your question about the Asturian, I was using Westphalian D, and somebody in a paper review chastised me for not using Asturian. And that's why I started to use Asturian. So now I'm still out in left field somewhere. Oh, well. Now, with regard to the correlation with Western Europe, I now have a set of 2 cores that goes through the entire Pennsylvanian and the Illinois basin. Now, they've taken all the coals for coal bed methane work, which is fine, because I'm using these cores to try to better document the changes going downward. And where we have a conspicuous lack of data is in the shales, going from at least in the Asturian / Westphalian D up. Okay, we simply don't know. Our late Pennsylvanian is very rarely studied because in the Illinois basin, we don't have any coal. Okay, there's nothing economic about it. It's red, and it's just something that they have to go through in places. In the Appalachian basin, same kind of thing. We have a lot of data on the Monongahela group because we have a lot of coal. Once we get into the Conemaugh, we lose the coal, and it just becomes, well, it was originally referred to as the upper barren measure. So in I maybe 2 years, but 15 months, I'm hoping, I'll be able to present something on a better refined correlation of what those cycles look like with comparison to Jeff's work in Western Europe. I know that's a real problem.
If I could just add, just briefly, but very similarly in Western Europe, in the Paralic area of Northern Europe, yes, through the same period, it's a very clearly defined aridification, if you like. The red beds start coming in at the top of Bolsovian, and you get more and more well-defined. And I'm unaware of any cyclicity that we see in that Paralic area north of the Variscan front. I'll be saying afterwards this afternoon, I'll have somehow or other make the point that on the southern side of the Variscan orogenic belt, there's a different Paralic system, which is where we define the Cantabrian, but that's a different issue.
Okay, are there other questions? I have a question then, maybe not fair. So Courtland, do these polynofloral changes you've shown, do they very closely track the macrofloral changes in the same sections?
In some cases, yes, in others, no. I don't know that. This is mostly in conversation with Mitch Blake. I get the feeling that we have a better level. We have a finer level of determination of biostratigraphy with the spores. But I'm thinking that's mainly due to I can pull spores out of a lot of things, not everything, but most things. And so it's rare that I find a lithology that, I'm not able to extract a meaningful polynoflora. But with the plant fossils, there's definitely spots where even if you find plant fossils, maybe they're not identifiable. They're just all macerated up. And so I'm just wondering if that's a taphonomic bias. Spores they're about they're the most the most resistant things I think I know of. I mean, I know when I prepare them, I'm pouring all kinds of acids on them and doing all kinds of just unsundry things to them, and yet you end up with stuff that is okay. So I don't know that I don't have a clear answer to your question.
I wonder, Bill DiMichele, Bill, can you comment on my question? I'm just curious because I think what you're saying, Courtland, is whatever offset, or maybe Herman can comment, whatever offset you're getting may be a taphonomic bias against the macro plants, whereas you have a more complete or comprehensive spore record. Is that kind of what you're suggesting?
Yeah, but I think it's just because I can get spores out of things where there's no plant fossils.
Right. So Herman has a comment.
I agree with Courtland.
Okay. So basically, let me see if I can walk away with this answer, that the macro plants don't really contradict the patterns you see in the spores.
No, not at all. Not at all.
But it's a less complete record, perhaps.
Yes. Yes.
Good. That's a good take home for me.
Yeah. If you really want to see me with egg on my face, okay, send me a red bed. Okay, Lynn Sorrigan can tell you all about her dissatisfaction with sending me red beds. Red beds, okay, anything with carbonate in it, okay. Polynomorphs are described as acid-insoluble microfossils, and they are. I've left things in hydrofluoric acid for 6 months, and they still look good. But as soon as you get a little bit of alkalinity in the system, my preservation goes away. And the last thing that is a limiting factor with palynology is just level of thermal maturation we refer to as coal rank. Mm-hmm. I can pull things out up through the bituminous coal rank, but when I get into medium volatile and low volatile bituminous coal, then I'm done with the coal. I can go a little bit further in the shales, but I'm basically, those are the three things that are real killers for polynomores.
Okay, well, we're out of time here. Thank you, Courtland, again, excellent talk and some good discussion.